And welcome everybody. Holy cow, it's great to have you here. It is Sunday, CCNA Sunday. I'm Keith Barker. If you're new to this channel, oh my gosh, so glad to have you. We do live streams periodically, at least once a week, sometimes three. And our focus today is going to be on the concept of QoS, quality of service. And also stay tuned after the this live stream. We'll cut it off formally, save that for YouTube for later ingestion, and then for later consumption, and then we'll stick around for those of you who are in the live stream, and we'll have some Q&A after for yesterday. We stayed for quite a while, had a great time, so we'll do that afterwards. All right, our focus today, and also I have a new camera that I'm testing out, so I always like learning, always continuing to try to improve and do better. So I've got a new camera right there, and I'm still dialing in the lights, and I think the secret, every day, if we just make small steps in the right direction, we can be very successful and get to our goals. I was talking to Jeff Kish, who's a dual CCIA, great guy. He streams and he's a gamer. It was amazing. Anyway, I was chatting with him, and he said that what he does, which is a great strategy, he says, Keith, I just list like 5 or 10 things that I want to do or accomplish or get done, and then I'll just tackle like 1 or 2 of those every week or when I have an opportunity, and he's going in the right direction. So whether it's a certification or getting better at something, just take the steps. And it's okay to make mistakes, because you make mistakes, they're not life-threatening, hopefully, and then you can continue going on in your journey. All right, our focus today is QoS, quality of service. It is certainly a topic on the blueprint for Cisco certification for CCNA. And so let's go to a whiteboard and talk about a couple problems, and then we'll talk about some solutions for it. And the objectives, also I want to point out that the objectives for this live stream, this recording, are 2 basic things, and I have my notes to keep us on track. Number 1, I'd like us to identify what is the problem with some apps as they communicate over a network. For example, email is an application that we can use that sends email back and forth. Things like these, like we're doing live streams, that's certainly an application. If we're having a 2-way phone call over an IP network, that's certainly another application of the network. So what are some of the problems that come up with those, and then how do we solve those? Those are the 2 things I'd like to tackle in this, and focusing on QoS as one of those solutions. So let me grab a pen, and here it is. Here I've got a pen. All right, so let's imagine we've got a user, and I'm going to put Gus at this computer right here. Gus is, what a great, you know what? I just enjoy meeting so many people, and occasionally there's just people that you meet where, I don't know, they're just so authentic and real and nice. And that's what I want this channel to be all about, is about people helping other people. So Gus, I'm using you in this example as a tribute to say thank you. Way to go. All right. So here's Gus at this computer, and Gus is going to communicate with a device over here in the branch office. So we'll put, I'm going to put, let me see who else is in here. How about James? James is in the queue. James is in the house. All right. So this is James and Gus, and they are going to have some communication over the network. And let's imagine it's file sharing. Great. So we're going to do file sharing between Gus's computer and James. Now, if we're using file sharing, if we were to draw inside of Gus's computer here, if we were to take a look at the protocol stack, so this is the TCP/IP protocol stack. At the application layer up here, Gus's, now, I wonder which application Gus is going to use for the file transfer. We could do it via HTTP. There's options for that with that protocol, or we could use a protocol called FTP, File Transfer Protocol. So that's an option. Let's use that option. So if we're using FTP, James has a server over here, or some software running on his computer, acting as an FTP server. All right, sounds great. And then Gus has an FTP client, and he is going to transfer a file from his computer over to James' computer over here at the branch office. Now, we'll talk about this connectivity in here in a second. So if we're using FTP, FTP is an example of an application layer service. So at the application layer of the protocol stack, the application layer service is FTP, and the software, this is important, the software that Gus is using at this computer is a program that is using the FTP application layer service. So maybe he has secure FTP or some other application, and he points to James' machine, and he says, send this file, And at the application layer, it would use the FTP application layer services of the network. And then the network next layer is the transport layer. I'll put it over here to make it consistent. So the transport layer, FTP, is an application layer service that uses TCP at layer 4. So if we were to take a look at a protocol analyzer, it would show us that TCP is being used at layer 4. And then at layer 3, which is the network layer, we're going to have IP information. So from Gus's perspective, let's say Gus is at 10.16.0.10. Hopefully it's okay, Gus. And James, you're going to be over here at, let's put you on a different subnet. Let's put you on, so let's say this is /24. And let's say James is over here at 10.16.1.0. I'm sorry. You can't have 0 for your last octet if it's a 24-bit address. So we'll give you .2, and we'll say /24. So what that means, if we are going to dissect that, that means that Gus is on the network 10.16.0 based on this mask. And public service announcement, join us for Subnet Saturdays and learn all about IP addressing. All right, now that's said, let's go ahead and continue here. So Gus is on the 10.16.0 network, his host ID is 10, and James is up here on the 10.16.1 network based on this mask, and his host address is .2 on that network. Fantastic. So Gus and James have each other's, or Gus has James' IP address. Maybe you got that from DNS. DNS is a great option to discover the layer 2 address or the layer 3 address behind a name. Or maybe we used something internal, or maybe just Gus just knew that IP address. And so in the IP packet, Gus is going to put his source IP address in the IP header and James' destination IP address in the IP header before he sends the packet. Now, next, wrong. Let me change that color. Just make it consistent here. Next, before Gus sends that packet on the network, he also needs to make sure he includes layer 2 information, and that's the data link layer. So this is layer 2, that's layer 3. So layer 2 is all about layer 2 addresses. And so since Gus is on an Ethernet network over here, Gus is going to include the source, let's see here, Gus source MAC address. And so that source MAC address would be put into the frame, and he would put the destination MAC address. And this is where it gets tricky because inside of this layer 2 frame, now I know there's many of you in the live stream right now, which I'm very grateful for, by the way, who already know the answer to this question. So if you would chat it in, I will take a peek over at that. What would Gus insert as the destination layer, I mean Gus's computer, what would he insert as the destination layer 2 MAC address in the frame? So at IP, it's going to be the layer 3 address of Gus. Destination is going to be the layer 3 address of James. But what is Gus going to use as a destination layer 2 address for the MAC address? And I'm going to pause just for a moment. There's a teeny bit of a buffer, like maybe 5 to 8 seconds between the time I speak and by the time it shows up on your screens. And so then there's also a response back. So my question is, what is the layer 2 address? Oh, right. All right. HK and Michael and Karthik and Rob. And I'm having a moment here because you're spot on. All those comments are saying, yeah, the layer 2 destination address is going to be Gus's default gateway to get off that local segment. And that's spot on. Layer 2 addresses are only good in that VLAN. And so Gus did this. Gus's computer said, okay, I need to send this packet, layer 3 packet, to a device on a different network. So if we look at the topology, Gus is on network 10.16.0. He knows that he's trying to reach 10.16.1 at a different network, and as a result, he needs to send it to his default gateway for forwarding. And so Gus is going to add the layer 2 address of his default gateway, and I love it that many of you said, yeah, and they actually told it what it was. So if this is gig 00 on R1, the layer 2 destination MAC address is going to be that interface's MAC address. Okay, now for bonus points, how in the world does Gus, if his computer doesn't already know it, how does Gus's computer know what the layer 2 address is of gig 00 on router 1, his default gateway? How does he learn that? It's a good question because all these pieces have to work for it actually to send traffic on the network. And as I'm looking at the responses come in, you're right once again. The way that Gus's computer would learn about that layer 2 address is ARP, the Address Resolution Protocol. Spot on. Yeah. So Gus's computer, if it doesn't already have it in the ARP cache, we'll do a ARP request saying, hey, I'm looking for the guy who owns this IP address, maybe that's .1, and please send me your layer 2 address. Router 1 responds back, and then Gus includes that in his future frames that he's going to forward over to James. Fantastic. All right. So, and then finally, Gus sends his traffic out on the network. Now, all that activity, all the thinking, takes milliseconds. Now, a millisecond is 1/1000th of a second. Just so it doesn't take a lot of time, but it does take a little bit of time. And so Gus's computer takes all that information and then starts spitting them out on the network into the switch. Then the switch, based on the layer 2 addresses, makes a forwarding decision, which would forward the frames addressed to the default gateway to the default gateway. R1 would look at that and say, hey, this is my layer 2 address. It would de-encapsulate it, open it up, look at the layer 3 destination address and say, oh, that's not me, but I'm a router and I'm enabled for routing. It would look at its routing table, make a forwarding decision. How do I route it in the direction that it needs to go? And then it would re-encapsulate it at layer 2 based on where it needs to send it and then send it on its way. So in this topology right here, router 1 would actually re-encapsulate it at layer 2 with the next layer 2 destination address being the firewall. Then the firewall would make the next layer 2 address be this router 2, and then router 2 would encapsulate that appropriately for the serial link, or if it's going over the internet, go that way. So maybe we have a VPN going this way, or a serial connection. Maybe it's point-to-point, or maybe it's frame relay. Stop the track. It's not going to be frame relay unless it's like 20 years ago. So we'll just forget I said that. So a serial connection of some type or internet, but it'll appropriately encapsulate that frame and send it on its way. Okay, fantastic. So what's the problem, Keith? What is the challenge here that could happen? Well, with a file transfer application like FTP, does Gus really care if it takes 2 or 3 seconds or 4 seconds or 5 seconds? Because if there's congestion on the network, meaning there's a bottleneck somewhere, maybe at the router or the firewall or even the switch, if push comes to shove and there's some congestion, FTP is TCP based. So if it's TCP based at layer 4, that means it's sending acknowledgments and verifying data got there, and if something is missed, it'll try again. Pretty robust, and I don't think anyone would notice if there was a delay of a second or 2 or 4 seconds even for an FTP file to be sent if there was congestion somewhere in the network. However, that story changes if we have a situation where we have Gus now talking over to James, but now we're using, and I'm going to go ahead and clear this off. We know it's Gus, we know it's James, we know the layers. But the problem is now, what if Gus and James are using voice over IP? And this is one of our goals of this session, is to identify some applications, some uses of our networks, which if we have a lot of latency or variable latency or problems where it's not going to work out well. So here we have Gus on computer 2, James is up here in the branch office. As they communicate back and forth, I'm guessing, and it's a reasonable guess, that when they're talking to each other, and maybe they're focusing on, hey, I'm focusing on the new CCNP, I'm going to be studying that, or hey, I'm focusing on, they're having a nice chat, and it can be video. So video and voice, or video chat or voice chat, either way, they'd like it to be relatively timely. So if Gus says, hi, how you doing? Good, yeah, I'm good, Gus, how are you doing? And then if there's huge delays, sometimes people are going to talk on top of each other unintentionally. So my wife and I have had that challenge with certain voice applications. And I just said, we're going to get a solution so that when we're not physically in the same location, we can use a solution that doesn't have a lot of latency, and so that we aren't going to accidentally talk over each other. Because there's a big gap, but the other person didn't really intend that gap. People can talk over each other. So anyway, word to helping your relationships thrive. You never want to talk over each other, and you don't want to accidentally talk over each other because of a latency issue with a voice over IP application. All right, so continuing on our discussion here. If we have no congestion in the network, meaning router 1 says, life is good, I have packets that come in, I forward them, and the firewall says, life is good, I have packets come in, I forward them. The router says, I get packets, I forward them. The switch says, I have frames that come in, I forward them. There's not really a problem. And so these network devices have the concept of a line. Now, when I say line, I want you to think of like a line at the bank. I'm not a fan of lines. In fact, if I go to an amusement park, I will usually strategically do the research and find out when is the least busy time, and then I'll go then. So like for Disney World, it's like in the first two weeks of February, and it's all, people have done the research and you get the data, and then you go at those times, because I don't enjoy a line. I just don't know. There's an exception to that. Sometimes lines are cool because, like, if I go to DEF CON here in Las Vegas, there's usually a big line for buying your admission pass to get in, and there's some fascinating people in the audience, or in the queue, in the line. And so sometimes lines are good. But generally speaking, from a network perspective, if there's a line of traffic that needs to be sent and it can't be sent because there's just not enough bandwidth to send it, somebody's going to go ahead and suffer. And so what they call this line, like in Europe, Simona, one of our trainers at CBT, she's great. Oh my gosh, she has the best words. She's so fun to listen to. If you're ever studying Microsoft or anything that she's teaching for that matter, it could be project management, anything, she's just a blast. She's just a fantastic trainer. But what she'll call a line, she'll call it a queue. Queue. So yeah, I got in the queue at the bank, or I got in the queue. So all these network devices have a queue. And that queue looks something like this. So let's imagine that this is the traffic coming in, and this is the interface that the traffic is going to be sent out of. So the router gets the packet, makes a decision, repacketizes it, or puts a new frame on it and forwards it out. So there's two parts of this. There's a hardware part of the queue, and there's also a software part. So if packets come in, just imagine that we're going to a grocery store or an amusement park, and they have this huge line, this huge space for a line, but there's no line. So you just basically walk through, and you get sent. So the thing about QoS is that if there's no congestion, if there's no contention for the bandwidth that's available, your router's not going to stick around and say, I'm just going to make that wait for a while. If there's only like 10 megabits per second of traffic coming in, and there's 100 megabits available, your router or switch or firewall is just going to send it. So the thing about quality of service that we're going to use to fix a problem with like a voice over IP conversation being held up or slowed down, it really only comes into play if we have congestion on our network, if there's a problem with a bottleneck. And with voice over IP or other real-time applications, what do you do? Because a phone call over a voice over IP is not going to be very good if we're dropping packets, if we have lots of latency. And so the thing with QoS, the problem is that some applications can't tolerate and survive bad latency or intermittent latency. So to solve that, we're going to use QoS. And that's two of our objectives. One is, what are some applications and problems of why we'd want this? And the second is, how do we solve it? The answer is QoS. My parents, my dad's 90 now, still doing great. My mom's in her 80s. They are, well, I won't give you the backstory on that, but they taught me in my youth about being fair and honest. I am very grateful for that discussion and that example that they set in my young life growing up about doing the right thing and treating people fairly, treating people equally. In computer networks, that goes out the window. Because in computer networks, if you and I know that, hey, there's some bottlenecks in our network, some congestion, and we know that there's some voice over IP traffic or other critical traffic that just has to go through, we need to have some mechanism of preferring that traffic and telling the router or the firewall or the switch to go ahead and say, you know what, if you ever see this traffic coming in, so first of all, I have to identify the traffic. And then if you ever see this traffic coming in, that big queue you have that's all full and people are having to wait to be sent, go ahead and just take that traffic and maybe move them to the beginning of the queue. Or like going to an amusement park when it's crowded and you have like one of those fast pass where you just like, whoop, there's a big line, but I'm going to the front. That's what it's like. Or we could make a separate line just for that type of traffic. So imagine an amusement park with a long line for normal traffic, normal people, that's not right. A long line for non-critical traffic, I can't say non-critical people because that's not real. Non-critical traffic, and then a shorter line that's just for special traffic. And then if you're that special traffic, you get in that special line, that special queue, and then it goes very, very quickly. And that's the concept of QoS. It's differentiating traffic and giving some traffic higher or better priority than other traffic on your network. Last night I went to, last night was great. I went to a play with my wife. In Las Vegas, there's a lot of small theaters that do really amazing plays with great people. Anyway, went to a play. It was fantastic. Then after that, my wife Dina had a friend from California. Her partner is he's one of the lead guitarist for a tribute band, not the Red Hot Chili Peppers, but a tribute band called the Red Knot Chili Peppers. And so, and part of that, we went in. We got there like 10 o'clock, and then Dina's friend found us, gave us these badges that got us backstage. And so we went backstage. It was great, but they just didn't let anybody backstage. You have to have that badge, that marking, that classification that you're okay to go backstage. And I got preferential treatment because of who Dina knew. Anyway, it was a lot of fun. So the concept of QoS is that if there's congestion, because if there's no congestion, boom, 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 we just send everything and life is good. But if there's congestion or bottlenecks on the network, QoS makes sure that we've identified traffic that's more important, and then we treat it differently. That's it. That's what the deal about QoS is. Now, there's several different ways of doing QoS, and I think we had to talk about a few of those because it'd be important to be aware of it. So let's go ahead and let me get out my drawing tool again, and let's talk about the basics of. Well, let's do first in, first out. First in, first out is a strategy. Let's pick on router 1 for this whole example. First in, first out simply tells the router, hey, you get a packet in, send it, right? Make a routing decision, send it. But if there is some congestion, here's the queue. So at the top end, we have this hardware part, and then we have a software queue. And so if there's congestion, basically start stacking up the queue. And then the first ones who got into the queue are the first ones who get out. That's how first in, first out works. We're not really differentiating any type of services. We're simply saying, yep, I got packets in. I'm going to go ahead and send them out. So if we need to change the rules for that, another option that we have besides first in, first out is called priority queuing. Let me get my notes here. I put these in a specific order. Priority. Priority. Yes, I can talk and write at the same time. So with priority queues, let's think of 3 different queues. I'll put another one here and another one here. So these are all queues. Let's imagine these are all going to end up going to the same exit interface. We'll call that egress because that's how we spell exit in Cisco. All right, so that's the outbound or exit interface that we have 3 queues. We'll call these queues A, B, and C. So with priority queuing, it's terrible, actually. All by itself, it's the worst. And here's why it's the worst. We identify certain types of traffic, and let's imagine that voice over IP is identified as our high priority traffic, and we assign it to this queue, QA. And then we do gaming traffic, and if we're a gamer, we assign that to QB, and then everything else we assign to QC. So this involves identifying the traffic first. You know, what type of traffic is it? We'll take a look at how to do that with access control lists or network-based application recognition and some other methods. But we've identified the traffic. We then assign it to a queue. And with priority queuing, oh my gosh, check this out. It's so unfair. Priority queuing says, all I'm gonna do is work on QA. I've got a feeling I can be good that way. To QA, yeah. So basically this queue right here, QA, which all the voice over IP traffic is in, gets all the treatment. Gets all the throughput. Well, what about the other queues? Okay, so the other queues, if there's nothing in QA at all, the initial queue, the first queue, it then says, okay, there's nothing in this top queue. I'm going to take a peek at the second one. It looks at the second one, starts to move some traffic, and once it's done, it goes back to QA. And then it moves any traffic there. And then if there's nothing there again, or if it finishes, it then looks at QB. And then if there's nothing there, it looks at QA. And then QB, if there's nothing there. So basically, QC has a really good opportunity of being starved, meaning the CPU and the router has no interest in really serving QC unless QA and QB, which are higher priorities, are empty. So we're not going to use priority queuing by itself because we can starve out other types of traffic. But it certainly is something to be aware of because it is a type of queuing. So another type of queuing, and I'm going to clear off the screen and we'll redo a couple of these. Another type of, so we have first in, first out. Then we have priority, which we just discussed. Another one is WFQ, weighted fair queuing. And I like this. I like weighted fair queuing. Weighted fair queuing goes something like this. I know there's a lot of traffic coming in, says router 1. And if I have the ability to forward everything, there's no congestion, I'm going to just send everything as it comes in. Pack it in, send it out, no problem. But if there comes a point when I have so much coming in that I can't possibly send it all, exactly as it comes in, I'm going to go ahead with weighted fair queuing. Is I'm going to identify flows of traffic. Flows of traffic. Now, what is a flow of traffic? A flow of traffic is like a session. Let's say you went to a website, and during that session between you and that website, well, you might have multiple sessions, but in one of those sessions with that website, you're going to have your source IP address, destination IP address, TCP ports, certain source ports, certain destination ports for that flow, for that session. And so the router with weighted fair queuing says, okay, I'm going to treat that as one flow of traffic. So maybe Gus and James have a session between them for their file transfer protocol. And maybe they have another session for their voice over IP. And maybe then Gus has another session going out to CNN or another website or whatever sessions he has in place. And the router, if there's congestion and weighted fair queuing is on, WFQ, it will say, I've identified each of these flows of traffic, and I'm just going to give them all equal bandwidth. So it would give your voice over IP call, that session, the same amount of bandwidth as it would for Gus's session out to CNN, as it would for the FTP transfer session. So I think it's fair. That's why they call it weighted fair queuing. Flows are identified dynamically just based on the IP addresses and TCP information and port numbers or UDP or whatever it's layer 4. And then it simply says, okay, I've got 15 sessions all going on. I'm just going to give them equal bandwidth per session. And that's good because if somebody's doing a huge FTP transfer and somebody else is doing a quick little DNS request, which is very teeny, weighted fair queuing is going to give that little guy, equal time in that whole flow of traffic so it won't be starved out. So we're not starving it anymore. So that's weighted fair queuing. However, the problem with weighted fair queuing is if Gus and James are having a voice over IP conversation and they're doing a file transfer, the voice over IP, if there's just not enough bandwidth at router 1, it may cause a problem with excessive latency on the voice over IP call. And as a result, the voice over IP call, even though the Cisco router is being fair, it might have a problem with the fact that the voice over IP call is not getting everything it needs. So to solve that, we have another option here, and that is called CBWFQ. And what that stands for is class-based weighted fair queuing. So think of it like this. It's weighted fair queuing, which is great, but we're also going to add the opportunity to create a special class and queue. So let's call this, I'm going to call this, you're special, so special, I gotta have some of your attention. That's why I didn't take a career in singing, because I can't sing. All right, so we have a special queue, and then we have everything else, all the other normal ones. And so what we can do with class-based weighted fair queuing is we can identify some traffic, like voice over IP traffic, and assign the voice traffic to that special queue, and then we can just, how do I say this gently? We can just be a little bit more generous regarding bandwidth for that special queue. So instead of weighted fair queue saying every flow gets exactly the same amount of bandwidth, we can say, you know what, for this special queue, we want to give it a little bit more or a lot more bandwidth. And then for everything else that you identify as flows, go ahead and be equal with whatever's left based on those guys. So we're being more fair, but we're able to prioritize just a teeny bit, well, actually quite a bit, that special queue. So that's class-based weighted fair queuing. So when you think of class-based, Like certain classes of traffic, certain identified traffic is going to get into that queue, and as a result, they are going to have some preferential treatment, at least here on router 1, as their traffic goes through the network. All right. There's one more I'd like to chat with you. Well, there's actually a couple more. There's one more I'd like to talk about now is like LLC. LLC. Keith, you've been working with some limited liability companies? Maybe. But this is LLQ, which stands for low latency queuing. And here's what low latency queuing is. Low latency queuing takes class-based weighted fair queuing and adds the ability for us to go ahead and add priority queuing to it. So remember back here, priority queuing, where we said, okay, this queue goes first no matter what, no matter what, no matter what, and then the other queues? Well, low latency queuing is taking the class-based weighted fair queuing, where we have special classes and being fair to everything else, and we have the ability to be more strict and give one of those queues priority, which means that that queue could possibly starve out everybody else. I mean, if we're saying this one queue with low latency queuing has a certain amount of bandwidth and priority and everything else, it's possible that all the other flows don't get any attention. So in addition to low latency queuing, there's also limits we can put in place. And the concept of limit is referred to as policing. So policing or policing the traffic says, okay, this is a priority queue up to this point. So up to 1 megabits per second or 5 megabits per second. So we're not just saying, yeah, this queue is the most important queue no matter what. We're saying this queue is getting special treatment. You want to take care of it first up to a limit. And then after that limit is met, it can go ahead and work with the others. So that's kind of like a good progression of queuing. So first in, first out, no prioritization. Priority queuing, one queue gets all the attention, and then if there's nothing there, it'll take a look at the other queues. Weighted fair queuing, individual sessions, every flow gets equal treatment. So an FTP session, a voice over IP session, and a telnet session or SSH all gets equal treatment. And then a little bit of prioritization for a certain class of traffic is class-based weighted fair queuing, where it gets a little more oomph and preference, and everything else is then treated equal. And then low latency queuing is adding the priority factor with limits, with policing to a specific queue, and then treating everything else like weighted fair queuing. So that's the progression of queuing. Let's talk about, I had a couple other things I wanted to mention regarding queuing. Oh, yeah. Regarding all these mechanisms of queuing, this is referred to as diff. I'll put that in a different color, make it stand out a little bit more. Let's go for this guy. It's referred to as differentiated services, or as his friends call them, Diffserv. And differentiated services simply means that when a device that has QoS implemented gets traffic, and if there's congestion, I mean, it can't send it out as fast as the queue is building up, the Diffserv says on this specific device, go ahead and use the queuing mechanism based on how it's been configured. And differentiated services is an example of per hop. So a per hop behavior. And let me explain why that might be really important to understand. Let's say Bob is, not Bob, it's Gus. Hey, Gus. So Gus is here, James is up here, and they're having some kind of a session between them. And Gus sends his traffic. Router 1 says, happy, no congestion here. No need to delay anybody or prioritize anybody or put something at the beginning of the queue because I've got bandwidth, and it sends it. That's because this is gig. Maybe this gig 00, and this is gig 0/1, so no bottleneck here. And then the firewall gets it. And this could be a numbered amount of firewalls. It could be the Firepower Threat Defense Appliance. It could be an older ASA. I shouldn't say older. It could be an adaptive security appliance. And the firewall, if it may have congestion. Now, if it has congestion here, all the quality of service that we put here on router 1, if we don't have those same policies about identifying which traffic to prioritize and then making preferential treatments on it, if the firewall doesn't have those same kind of rules, we could have congestion here, and as a result, what we prioritized on the router wouldn't be prioritized on the firewall. They're separate devices. And so we need to also make sure we implement the policy here for QoS. So let's imagine that this firewall has been configured So we've done 3. And there's 3 basic things we need to do with QoS. One is identify the traffic to be treated special. That's called classification. The second is we need to go ahead, is to mark that traffic, put labels on it so that everybody in the network knows it's special. I mean, if we have, let me get an example with cups. All right, packet A, packet B. These packets are coming into a router or a firewall. How does it know which one is supposed to be prioritized? So a key element is identifying the traffic that should be prioritized and also marking it by putting labels on it. So we could have this labeled as high priority traffic or super important traffic, and we use bits in the IP header to do that, and they're called DSCP markings. But we put markings on this packet saying, hey, this is marking A, and this is marking B, and that way when the firewall or router gets it, it can say, oh, I've got congestion, here's my policy, I'm putting this one first, and then this one later, or based on the policy that we have set. So the elements are identifying the traffic, having the correct markings in the IP headers or in layer 2 trunking on the layer 2 headers with COS, and then having a policy that says on each of the devices, okay, if there's congestion, here's what I'm supposed to do. I'm supposed to put this type of traffic in this queue, or I'm supposed to prioritize this traffic and then send it out ahead of other traffic like an FTP transfer that may not care that much about the flow or not be interrupted by the flow. All right, so going back to this. So we have the firewall with QoS. Now, if the router, let's go ahead and take off the internet here for a second. We have this slower link here. There's bound to be congestion here. If we have high-speed Ethernet, gigabit, and all the way in our internal network, and then we have this serial. This lightning bolt represents a serial connection. If this is like, 1.54 megabits per second, which would be an example of a T1 type of speed, there could be a lot of congestion here. So we'd also need to make sure we implement the quality of service here on router 2. And it should be the same policy. And that's why it's referred to as per hop behavior with differentiated services, because we need to make sure all the routers and switches and firewalls agree on identifying what type of traffic, which could be based on their markings, which is a great way to do it. So we could have, for example, this router, as traffic comes in from Bob, we could have this router in charge of marking the traffic. And so as Gus's voice over IP traffic comes in, it can be classified as voice over IP with certain markings. And as Gus's FTP session comes in, this router could mark that traffic as a different bits in the IP header for the purposes of prioritization on the other devices. So we'd want to classify the traffic, mark it, and then train all the devices to behave a certain way regarding QoS when they see that traffic if there's congestion. So let's talk about for a moment something called the MQC. So MQC is an acronym that we may see from time to time. It stands for the Modular Quality of Service Command Line Interface. And it basically is a great way of thinking about the implementation of the 3 elements that we need to do with quality of service. And it uses 3 elements, and I'll put them right here. Class maps. And what class maps, you might say, well, Keith, what does a class map do for a living? A class map is used to identify traffic. So here on router 1, as that traffic is coming in, Gus's traffic, if it's voice over IP traffic, a class map could identify, okay, based on the ports and protocols and so forth, or the VLAN it came in on, it could identify that as a certain type of traffic, and then it could go ahead and actually mark that traffic. So the class map is used to identify the traffic. Then we have something called a policy map. So the class map is saying, okay, identify the traffic. The policy map says what to do to that traffic. So the actions could include things like put this in a certain queue. Or the action could be add these markings. Or the action could be add these markings to the IP header for the benefit of the rest of the network so they can look at those markings and put it in a certain queue. Like in class-based weighted fair queuing or low latency queuing, to put it in the queue that's appropriate for that type of traffic. So the class maps identify, match on the traffic. The policy maps say what to do as an action item when they see that traffic. And then the third element, which is really important too, is to go ahead and apply it. And that's applied with a service policy. So the service policy simply says where to do it. So if we had a class map and a policy map, so what traffic to look for, what to do with that traffic, and then where to apply it. On router 1, we could say we want to apply this inbound on gig 00. And that would be an example of how we apply it with the service policy. So that's the three main elements of the modular the modular QoS command line interface. Now, one of the realities is that I learned about maybe 20 years ago regarding QoS. And by the way, I had a really good opportunity to brush up on this to teach it today. So thank you for the request for QoS. Was that implementing this consistently across an enterprise at the command line is a near impossible task. Because you have to have, first of all, a plan. Like, okay, how are we going to mark these packets at layer 3? And, what markings are we going to use? And there's a whole laundry list of types of assured forwarding markings we can use by messing with the bits. And then, after that's done, implementing that policy across your whole network, all your devices. And that's where network automation comes in. And that's where software-defined networking is going to be very helpful, because we can identify policies of how we want certain types of traffic to be treated. And instead of going to the command line interface with class maps and policy maps and then service policies with APIs and scripts and a command center, we can say, here's what we want to have happen. And then we can just rain it down on the entire network topology. It also can report to us. So it's important to understand the basics of the options that we have, but I also want to make sure you're clear that in a production environment, doing this device by device by device it's no longer practical or realistic because the per hop behavior says we need to make sure every device agrees, that we agree on the markings that we're going to use, we agree on the type of quality of service we're going to use everywhere. So if you miss one place, like if we just forgot to do router 2 and we implemented class-based weighted fair queuing and we forgot to do router 2, Gus's call, as he talks to James over here with his voice over IP traffic, this is going to be a huge bottleneck. And if there's not enough bandwidth to go around, and he's using the default of first in, first out, or even weighted fair queuing, it's very possible that Gus's and James' phone call, their voice over IP session, is going to not be acceptable because of the slow connectivity here, relatively slow connectivity, if there's contention on the link. All right, let's talk about 2 more concepts, and then we'll close off the stream, and then I'll stick around for Q&A. So let me go ahead and clear this off. And the last 2 things I'd like to chat about is prevention. So how do we prevent congestion on the network? A few options come to mind. One, we just tell everybody, hey, just stop using the network. Not likely. Also, we could ask our users politely, please don't use these applications. Probably, if we don't enforce it with technical controls, probably not going to happen. So quality of service is important if we want to make sure that applications like peer-to-peer file sharing and gaming or so forth, if that's not our production network's core purpose, we might want to set up priority queuing or QoS so that we're giving a little bit of bandwidth to those other applications, but making sure that our core applications, whatever our company's doing, is getting the bandwidth that they need. So what if we've done all that and we have a problem with still too much congestion and we'd like to prevent it? And the way we can do that is with a process called WRED, which stands for Weighted Random Early Detection. And this is referred to as congestion avoidance. This is where we're taking proactive steps. Things are getting busy, and we want to stop it or slow that busyness down before it becomes a problem and everybody has a degradation of service. And it's based on how TCP operates. So when Gus and James are communicating in the TCP/IP protocol stack, if they're using TCP at layer 4, so they might be using HTTP or FTP or HTTPS or any other application layer service that's using TCP. TCP uses a window size, and in that window size, it does this. It's like Gus and James are chatting and are having a conversation with their FTP application or whatever it is, and as they're sending segments of data at layer 4, there's going to be periodic acknowledgments. So Gus sends a segment, and James says, "Hey, yeah, I got it, thanks." and they're tracking all those with relative sequence numbers. And then Gus says, that went so good. Maybe I could send 2 segments or 3 segments or a quantity of segments before I get an acknowledgement. And so he could send 2 or 3 or 4, send them over, and then James could just send 1 response. That's an option. And then if there's any missed, they can communicate that and pick up where they left off. But that's referred to as a sliding window. So that window, how many segments or how much data can be sent before an acknowledgement, is more efficient. Because what's more efficient doing this? Segment acknowledgement, or 10 segments, 1 acknowledgement saying, yep, got all of them, continue on. So there's a sliding window that goes up and down. That causes a problem, or can cause a problem, if we have a whole bunch of devices that are all communicating and there starts to be congestion on the network. I'm going to use this line right here as bad. So that's the bad line. So as more and more devices are talking and the window sizes are getting bigger and they're sending more and more data, it gets bad. And then, unfortunately, everything above the line, if there's a queue, here's the queue. So here's the hardware portion, here's the software portion, traffic's going in this way, going out that way. What happens if the queue totally fills up? So it's just let's talk about that. What do you do at the bank, or an amusement park, if they have a line for 100 people, and you show up and there's no line, there's no room left? Now, at an amusement park, they'd probably just wrap you around the Matterhorn, right? Just keep walking to the parking lot. You'll get in that line eventually. But in a queue for a Cisco device, once that queue is full and there's more traffic that shows up that needs to get sent, it's called a tail drop, which is bad news. Tail drop simply says, not only are you not getting in the queue, but I'm going to even forget you ever existed. Tail drop. And that's when the queue is full and there's no more room in the queue, and the router says, I would love to process you and put you in line, but there's no more room in my software queue. There's no more room in the line. So to prevent that from happening, and that would be what's happening right here, I'll put it in red. So this is where we have tail drops because the router can't process it anymore. And then what happens when we have these tail drops, Gus and James and all the other people that are communicating, put a little S there, Gus and James who are communicating, their computers in the background will say, whoa, we're missing segments, and they'll start decreasing their window sizes, they'll slow down, and so the traffic on the network goes like this as it slows down. And then as things go better, they go up. Once again, we have some drops because of the congestion, and then we have the network that settles down, it goes like this, and then one more time just to make it nice and symmetrical. So that just repeats. That's kind of a sawtooth pattern that we could see. Now, I want to point out this space right here. This represents bandwidth that could be available. So the whole network's slowing down because there was all these problems and congestion. And if we want to solve that, how do we solve that? The answer is a little bit, not difficult, but it's a little bit, unfair. So here's how we're going to do it. We are going to identify traffic that, if we start to get to the top where we're starting to have serious congestion, we're going to identify some TCP traffic that we can kill. So imagine that we're getting to the top, near the top of the threshold, and we want to use this feature called weighted random early detection. And what it'll do, it'll say, okay, great, I see these new packets coming in. They're new TCP packets, and based on identifying certain types of traffic, like, oh, that's a TCP packet for an FTP session versus that's a TCP packet based on another real-time application. Based on what we specified, it'll go ahead and take a look at FTP. I'll use FTP as an example. It'll take a look at all the FTP traffic that's trying to come in and then randomly drop them. So even if there's like a little bit of room in the queue left, it'll just simply say, well, I'm so close to my threshold, I'm going to just randomly pick FTP traffic, TCP segments. So in the IP packet, it points to TCP, and at layer 4, it points to the layer 4 protocol. That's how it sees it. And it just starts dropping them. No queue for you, no queue for you, no queue for you. So it just drops them randomly. So we're not killing just one session. We're just randomly interrupting the flow for many FTP sessions because that's the protocol that can survive it and no one's going to really care. At the same time, we never hit that maximum. So it's beautiful because we never get to a point where everybody, all the TCP sessions that are now have huge window sizes all have to go start shrinking. The ones that are important and have big window sizes can continue. The ones that were less important traffic, they'll recover, they'll be fine, and then they can start, reestablishing their smaller window sizes because they have some drop packets. And that's how we can prevent some congestion for TCP-related traffic with that technique called weighted random early detection. So that's how that works. All right, I'm going to share one more with you, and then we'll close it off. I'm going to grab my pen. I am going to clear the screen once more. And the last one I'd like to chat with you about is shaping. And I will use a different color for that. And for shaping, let's talk about router 2 for a moment. Let's imagine router 2 has a connection to a service provider. And it's not too hard to imagine because it's right here. So as router 2 is connecting, and maybe we'll just get rid of the serial link, and maybe router 2 is peering with the service provider, and in the background, so he has an Ethernet connection. In the background, the internet service provider could be using a number of things, including MPLS with traffic engineering or whatever they want to do in the background. It's transparent to the user to forward that traffic up to the branch office. So from our perspective here, we'd have router 2 connected to the service provider and the internet, the branch office connected to the service provider and or the internet, and then they could have logical connectivity between them. Maybe we have a VPN there over this internet. Okay, so the thing I want to point out is this. If this is a 10 megabit link, 10 megabits per second. Actually, you know what? We're not using 10 megabits too much anymore. Let me clear that off. Let's make it extreme. Let's say this is a gigabit interface. So that's gig 1/1 that we're connecting into the service provider's termination point. So we've got a physical interface, gigabit, but the service provider is only giving us 5 megabits per second. That's what we're paying for. So what happens if we try to send more than 5 megabits of throughput on this interface? The answer is it's not going to work for very long. We might have some bursts that are capable and so forth, but it's not going to be very good. Or if the service provider may say, well, if you go over this threshold for a period of time, a matter of seconds or minutes or hours, or they're averaging it, we're going to go ahead and charge you more, charge you a premium. So what we could do on router 2 is we could use the concept of shaping. Now, shaping simply says to the router, listen, I know, you've got this huge interface, right? Gigabit, and you can just like send all this data down. You have the ability. I'm giving you full creds for that. However, on the other side, it's not prepared to have you send all that at that throughput, meaning that much data, real data being sent in packets. And if you do, it's going to cost us money. So either way, whether they can't receive it that fast or they're going to charge us through the nose for it, pay through the nose for it. Anyway, we want to go ahead and bring that down. So shaping is the concept with, and it is in the QoS family, of saying, dear Mr. Router, on that exit interface, gig 1/1, what we want you to do is when traffic comes up, go ahead and have the queue, but as you send it out, we are going to have you slow down. So basically it's saying slow down and send that traffic out. And then in that queue for traffic shaping, you can also specify all the bells and whistles of details regarding who gets to send traffic, who doesn't get to send traffic. But the idea with traffic shaping is we're not dropping or killing packets that are trying to be sent. We're just smoothing them out, making them slower. The literal packet isn't slower. I mean, this packets travel over a wire at the speed of light times 0.8. But anyway, so the actual packets themselves, boom, 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 they're not really slower, but the throughput will be slower because we're using traffic shaping. And that's the concept of traffic shaping. In the old days, I'm going to mention it twice now, but in the old days when we had frame relay, we had a hub site and spoke sites, and they were, we had data link connection identifiers and these PVCs, permanent virtual circuits. We might have a headquarters site that had the hub site where it had T1 speeds, and then each remote site had 64 kilobits per second. I don't know, old school. And that's where it became really important to make sure that the headquarters site with traffic shaping wasn't just going to try to send all the data at once down to these little spokes, because they would not be able to handle it, hence the idea about traffic shaping. All right. Let me just check my list and see if I covered everything that I intended to in this discussion about an overview of quality of service with Cisco. All right. Okay. We want to take a look at the problems that could come up with networks where there's congestion. Great. So if there's no congestion, no problem. We just send it. So adding bandwidth everywhere is great, but not always possible or practical. And really, it's the weakest link in the chain that's going to cause our problems. So the problems are applications that suffer because of bad QoS, and the solution is to implement quality of service. Quality of service is differentiated treatment of traffic, and there's three basic aspects to it. Number one, identify the traffic. Like, oh, this is voice traffic, or this is FTP traffic, or this is a scavenger class of traffic. Maybe it's all the stuff that you really don't care about too much, but you want to identify it. And then secondly, we're going to go ahead and specify what we want to do with it. Now, that could be prioritizing it, or for at the edge of the network, it could be adding the marks at the IP header information for other devices' benefits, so they can look for those marks and then forward that traffic based on queuing that you specified. And then the third is to tell the network in every device that traffic goes through, including the layer. And layer 2, it's referred to as class of service marking. But anywhere you want that prioritization or that certain treatment, you need to implement across your network. So that's how it's done. And then I talked about the modular QoI, the MQC, with class maps, policy maps, and service policies. And then we mentioned it's per hop behavior. So every router or every device in the path needs to be aware of this game. Look for the markings on the packets, or layer 2, look for the COS markings in the 802.1q headers, and then act appropriately. And then we mentioned priority queuing, which is giving everything you got to one queue. And if there's anything left, then look at the other queues. Not good by itself. Weighted fair queuing, we talked about. Then class-based weighted fair queuing, which gives a little bit of priority and a little more benefit to one class of traffic, and then it's fair for everybody else. And then low latency queuing, which is adding the priority element within class-based weighted fair queuing for that traffic that absolutely must be able to be sent when it shows up at the router. And we also can put limits in place with policing, so that we don't have a situation where, even though we're using some priority options inside of our class-based weighted fair queuing, that one queue isn't going to starve out everybody else. And that's done with policing on top of the actual queue. And that's called low latency queuing. Then we took a look at shaping and weighted random early detection. So those are all the pieces I wanted to talk about today. I appreciate you joining me for the live stream on an overview of QoS. Our next 2 streams are coming up. It is Sunday today, so our next one's on Wednesday. We'll have another couple on Saturday and Sunday. I'll put those in the social. I'll have them recorded for you in the associated playlist as well. So for everybody who's in the live stream right now, which, wow, it's like, wow, it's a lot of people, over 100. Fantastic. For everybody who's in the live queue, in the live stream right now, stick around for like 2 minutes, because after I play this closing music, I would love to stick around and hang out and chat and answer any questions that I can that you might have that you want to put in the Q&A. So thank you very, very much. I appreciate you being here, and I'll see you, my friends, in the very next video. Thank you.